Hello again. We are continuing our discussion of differential equations. We've talked about one kind of differential equation, how to identify it and how to solve it. And today we're going to be talking about how to identify and solve a different kind of differential equation. These are called linear differential equations. So let's get started by talking about how to identify when I have a linear differential equation. If I have an equation that is either written as or can be rearranged as dy dx plus some function of x times y equals some other function of x, then I have a linear differential equation. All right, but it would be a lot nicer if I had a function like this and I converted it to a function that looked like this. Some function f of x times dy dx plus the derivative of f times y equals that q function on the right-hand side. Why would that be a nicer thing to deal with? Well, if you look closely at the left-hand side, I've got an f function times the derivative of y plus the derivative of f times just regular y. So it's of the form f times g prime plus f prime times g. That is product rule. So I want the left-hand side to look like something that has had the product rule done to it when taking the derivative. All right, so that when I integrate it, the antiderivative of that would just be the f function times the g function, or in this case, f of x times regular y. And then I could integrate the right-hand side by just figuring out the antiderivative of that q function. All right, and then if I wanted to solve that even further, I could divide both sides by f of x, and I would get that y equals the antiderivative of q all over the f function. All right, so that sounds easy to do, but how do I actually do that? How do I make that function look like that? Well, I start with what every linear differential equation looks like, and then I'm going to multiply through every term by some function of x that I create called I of x. So the first term will become I of x dy dx. The second term will become I of x times p of x times y, and on the right-hand side I will have I of x times q of x. Now I need to create this so that I of x is just I, which it is, no work there. Dy dx is y prime, which it is. And then in the second term, y is just y. But that I of x times p of x, that has to equal the derivative of the I function that I create. So how am I going to make that happen? How am I going to create a function so that the derivative of it is equal to the original function times that other function that was in the original question? Well, let's talk about how to deal with this in every case so that I can, instead of a specific case, so that I can deal with it with every possible linear differential equation. So I know that I want I prime to equal the original I function times the p function that was already in the question. If I divide both sides by I of x, then I get I prime over I equals p of x. And then if I find the antiderivative of both sides, I look at the left-hand side and I notice that I've got a function that has the derivative on top and the original on the bottom. Well, I know from my work with derivatives and antiderivatives that that has to be the natural log of I of x. And then without knowing what that p function is, I know that the antiderivative will just be the antiderivative, and I'll have to figure that out. Then if I want to figure out what I of x is, I have to undo that natural log. So I raise both sides as an exponent of e. So the left-hand side just becomes I of x, and the right-hand side becomes e to the antiderivative of p of x. All right, so that is always what I will create my I of x to be, is e to the antiderivative of the p function that's already in the question. All right, I'm going to call that my integrating factor. It's going to allow me to integrate this equation a lot more easily. So let's do an example to see how that's done. I start with cosine of x dy dx minus 2y sine x equals 3. X is going from negative pi over 2 to pi over 2, not including those endpoints, and y is 1 when x is equal to 0. So first of all, in order to make this look more like a linear differential equation, I have to divide by that cosine x that's sitting in front of dy dx. dy dx can't have anything in front of it when I start. So if I divide everything by cosine x, then I get dy dx minus 2y sine x all over cosine x equals 3 over cosine x. I can simplify both of those new terms by writing dy dx plus negative 2 tan x times y equals 3 secant x. So now I'm going to figure out what my integrating factor, my I of x, actually is. I know that the p function that was in the equation, it's the thing that's being multiplied by y, that is negative 2 tan x. So my integrating factor is going to be e to the antiderivative of that. It's going to be e to the antiderivative of negative 2 tan x dx. I'm going to move the negative so that it's right beside tan x because I know what the antiderivative of negative tan is. That is the natural log of the cosine of x. So my integrating factor is going to be e to the 2 natural log cosine x. And if you remember your rules for natural logarithms, that 2 that's being multiplied out front can actually become an exponent of your argument. So my integrating factor is going to be e to the natural log of cosine squared x. And knowing that e and natural log cancel each other out, I know that my integrating factor would have to be cosine squared of x. So all I've done so far is figure out what I have to multiply every term in the original equation by in order to solve it. So let's see if I actually accomplish that. There's the original equation again after I had divided out that cosine x that was originally there. What I'm going to do now is I'm going to multiply every single term by cosine squared of x and see what happens. Well, the first term becomes cosine squared of x dy dx plus negative 2 tan x times the cosine squared of x times y equals 3 secant squared x times cosine squared of x. And now I'm going to see if any of those terms can actually be simplified. Well, the first term can't be, so it stays as cosine squared of x times dy dx. The second term becomes negative 2 sine x cosine x. The y stays as y, and then on the right-hand side, that simplifies to be 3 times the cosine of x. Well, if I look at what I've created on the left-hand side, I do have a function f, which is cosine squared. And then the derivative of cosine squared is, in fact, negative 2 times sine x times cosine x. All right, so I've created what I wanted to create. So now I can find the antiderivative of that by just writing down the antiderivative is whatever my f function is times whatever my g function is. Well, my f function is cosine squared and my g function is y. So integrating the left-hand side, I get y times cosine squared. All right. So I get y times cosine squared x on the left-hand side, and then I still have to figure out what the antiderivative of a 3 cosine x is on the right-hand side. Well, that's actually pretty easy to do. The antiderivative of 3 cosine x is just 3 sine x. And remember, I have a plus c there. Now I'm going to plug in my boundary condition that I was given at the very beginning of the question where x was 0 and y was 1. So I plug that in. Everywhere there's an x, I put 0. Everywhere there's a y, I put 1. The left-hand side is just 1. The right-hand side is just c. So that means that c is equal to 1. So my final equation after I plug those in is y cosine squared x equals 3 sine x plus 1. Well, I'm not done yet because I haven't solved for y. So I divide both sides by cosine squared, and I get that y equals 3 sine x plus 1 all over cosine squared x. And you can split that into 2 terms if you want, but you don't need to. So we have successfully solved a linear differential equation. We will be doing more of these in class. If you have any questions, please let me know, and I will see you tomorrow.